right, ladies and gentlemen, let's talk about modeling specific with exponential and logarithmic functions. Now, when you're looking at a table, you can determine the type of function from the table. What you do is you look at patterns. You look at patterns in your input and then patterns in your output, okay? So if you have a linear function, you'll have addition in the input, which is your x. Let's write that down, which is x. And you'll also have addition as the pattern in your output, which is y. And that's what makes it makes a slope, essentially. Now, quadratic and exponential will not have a slope because they're not linear. They don't make straight lines. But quadratic will have addition in the input, and then if it does have addition in the input, it'll have a common second difference. We'll look and see what that is. If it's exponential, again, if there's addition in the input, then there'll be multiplication in the output. I do want to add cubic here. So all of your power functions, quadratic is a power function, cubic, quartic, all of those will have a common difference. So and if it's cubic, it'll have addition and then it'll have a common third difference, all right? And so on and so forth. So I want to add that in there. Let's look at some examples so you can see what happens. Now here's the thing. You're only going to see these patterns if you have addition in your input. If there's no addition in your input, you won't see that pattern. You would need technology of some kind or a graph to try to find the pattern. Okay, that being said, let's look at these examples. So in order for me to see a pattern, I have to have addition in the input. So first I'm going to check my input to see if there's some sort of regular addition there. So from -2 to -1, I need to add 1. If I add 1, I go from -1 to 0. If I add 1, I go 0 to 1, and I would add 1. And so it looks like I have regular addition in my input. Okay, so since there is regular addition in my input, I can look at the output and find the pattern. So to get from 0.5 to 1, I can do that by multiplying by 2. Let's see if that pattern persists. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. And it appears that that pattern exists all the way through. So I have addition and I have multiplication. So this must be an exponential function. All right, let's look at another example. So here, remember, I can't see a pattern unless there's addition in the input. So let's check our input first. So to get from -8 to -6, I would add 2. To get from -6 to -4, I could also add 2. Let's see. And it looks like I do have consistent addition in my input. So we're good there. So I can now start looking for the output pattern. Well, and this is where it can get a little bit tricky. So I'm going to just think to myself, could this be multiplication? Well, if it's multiplication, I should be multiplying by the same thing every time. Well, to get from -1 to +8, I'd have to multiply by -8, right? But 8 to 7, that would not happen multiplying by -8. So that's not going to be good. So it has to be some form of addition, right? Now it's either going to be what we call addition each time, or it's going to be a common second difference. In any case, I need to look at the addition to figure that out. So let's look at that. So what do I add to -1 to get to +8? I would add 9. To get from 8 to 7, I would add a -1. From 7 to 2, I would add a -5. And I would go on to see what that would be all the way across. Now, if this addition were the same all the way across, I'd say this was linear. Oops, this was add. I forgot to write that down. This addition is not the same all the way across. So let me do the second addition or difference, however you want to think about it. So let's do another line. What would I add to get from 9 to -1? Well, I would add -10. -1 to -5, that would be -4. 2, Negative 3 to 5, I'd add 8. Negative 3 plus 8 is 5. 5 plus 14 is 19. Again, these numbers are not consistent, so I need to try again. I would have here, so negative 10 to negative 4, I would add 6. Negative 4 to positive 2, I'd add 6. 2 to 8, I add 6. 8 to 14, I add 6. Now I have a common addition value. So that is going to be, this is called your common difference right here. So I have 1 line of addition, 2 lines of addition, 3. So this is my third line. So this would be it's called the third difference. So what this would be said is it'd be called a common third difference. Because I had to do this activity 3 times, and it's the third difference, this would be cubic. So this is a cubic function. The reason it's called the common difference is because you can subtract to get it. I like to think of it as addition, but you can think of it this way. Negative 1 minus 9 is negative 10. Negative 5 minus negative 1 is negative 4, and then you would subtract. So then negative 4 minus 10, minus negative 10 is 6. 2 minus negative 4 is 6. 8 minus 2 is 6. So you can think of it as a difference. This common multiplier right here, that is referred to as the common ratio. It's called the common ratio. That's interesting as well because a ratio is division, right? A ratio is a fraction, which is division. And we're actually multiplying to get that number. And the reason that is because if you were to divide, if you were to go right to left, you would have division, right? So 16 divided by 8 is 2. 8 divided by 4 is 2. 4 divided by 2 is 2. 2 divided by 1 is 2. And that's why this is called the common ratio. This would be called the common, this one down here is our common third difference. So that would make this cubic. Now remember, the patterns are one of two things. They are either multiplication or they are addition. So that's what I'm weaseling out of this. Now, I have to have addition across my input or my x values in order for me to see a pattern from the table. So here I'm adding 5, 6 to 11, I add 5, 11 to 16, I add 5. All right, so that's going to be the same all the way across. So since I have a common addition all the way across, I should have some sort of pattern in the output here. All right, that was add. If you don't have that addition straight across on the top, you're not going to see that pattern in the output. So it's very important that you check for that addition before you start looking for the output pattern. All right, so 0 to 3. Now, there's nothing I can multiply by 0 to get 3, so I'm going to say this is probably an addition problem. So from 0 to 3, I would add 3. Excuse me. To get from 3 to 6, I would add 3, and so on and so forth, and that's going to match all the way down. You can double check that yourself. So since I have addition in my input and addition in my output, this is linear. And the difference in these we call the slope, right? So your slope is the change in y over the change in x, or the difference in y or the difference in x. 6 minus 1 is 5, 11 minus 6 is 5, right? And then we have 3 minus 0 is 3, 6 minus 3 is 3, 9 minus 6 is 3. So our slope would be 3 over 5. So even though the pattern itself is addition, again, we're referring to subtraction when we're looking at that common change. And that's how you know it's linear. It has that beautiful slope. One more example. Remember, I have to verify that there's addition in the input, or I cannot find a pattern in the output. So first I want to see if there's some sort of common addition, or it's actually called first common difference if you really want to know. That common right here. So I have negative 2 to 0, I'd have to add 2. 0 to 2, I'd have to add 2. 2 to 4, I'd have to add 2. And I do get this question a lot. Do I have to check all the way down? Yes, you actually do. Because remember, If this addition pattern doesn't exist all the way down, you cannot see the pattern in the output. So you do need to verify that in your table that addition pattern exists all the way across. Then here, I'm either going to add or multiply. Okay, so 2, if I were to multiply, I would do 2 times 0 to get 0, right? And then if I were to multiply again, there's nothing times 0 to give me 2. So I know this is probably not multiplication, so let's go back and try addition. So 2 to 0, I'd have to add a negative 2. To go from 0 to 2, I need to add a 2. 2 to 6, I need to add 6. And this would be my addition all the way down. This is not common, so I need to do another line. So to get from negative 2 to 2, I would have to add 4. From 2 to 6, I'd have to add 4. 6 to 10, I have to add 4. 10 to 14, I add 4. This is common, and that's my second row. So I have a row here and a row here. So this happens to have a common second difference. If it has a common second difference, it's going to be something like x squared or quadratic. Okay, let's see how to find an equation for an exponent using 2 points. Now we've done this for lines before, let's do this now for exponential functions. So in order to do that, they will give you the form they want it in. They want it in this form right here with an initial value for a, and then they want a base, okay? It appears that though there will be a vertical stretch compress right here for that a value, they don't want any other transformations in that function. So that's what we're going to go with. Now there are 2 steps to this. Step number 1, you solve for a, so we're going to find a. And then step number 2, we're going to solve for b, which makes sense because in any equation I need values for a and b. I can leave in the x and y, right? But I need values for a and b, so let's find them. All right. Step 1, we're going to find a. We're going to use this equation here, a times b to the power of x. Here we go. Now I'm going to use this first point in step 1. You can use either point. I just like to use the first point in step 1 and the second point in step 2 because it makes sense to my brain, but you can switch them out. So I'll let this be my first point. Points are written x, y, so 1 is my x and my y is 6. So now it's, oops, I wrote that backward. 6 equals a times b to the power of 1. Cool, well, b to the power of 1 is b, so that's not bad. I need to find a. In order to do that, I'll divide both sides by b, so 6 over b should be equal to a. That makes complete sense. Fantastic. Now I'm ready for step 2. For step 2, I'm still using that same equation, y equals a times b to the power of x, but now I'm going to use point 2 for step 2. So here's my new x, here's my new y. So y should be 54, right? And I have an a is 6 over b, so that's cool, 6 over b times b to the power of x, which is 3. Well, fantastic, that's great. Well, b to the third divided by b is b squared, so that's 54 equals 6 to the power of b squared. Great, if I divide both sides by 6, I find that 9 is equal to b squared. If 9 is equal to b squared, then 3 must be equal to b. Now, I do get this question, should it be positive or negative? They've not asked us for any other transformation, so I'm going to use the positive option for b. Just because the way that this parent function was set up, they aren't asking for anything. And your b is usually positive. I'm trying to think. I don't know that I've ever had an instance where b was negative, so there you go. Not in Algebra 2 anyway. So my equation then is going to be y equals a, which, well, if b is 3, then a must be 6 over 3 is equal to a. which is 2. Yeah. So A is 2, and B is 3, and all of that is to the power of x. So that's my solution. I need to check my work on that. So the way that you would check that is you would just plug those numbers back into the equation and make sure that they check. So what you would do, assuming you didn't have a calculator, right, is, because you could use your calculator, you could graph it and see if these points are in your graph, absolutely. If you don't have a calculator, what I want to do is take these points and plug them back in. So the first thing I'm going to do is check point number 1. So if 6 is y, then this should be equal if x is 1. 3 to the power of 1 is 3, so that's 6 equals 2 times 3, which is true. So it does work. Remember, both of these points should be on there, so I need to check it twice. I'll do my second check. I'm going to take this equation. It should work when y is 54. And when x is, oops, that should be a 3. 3. Cool. Well, 3 to the power of 3 is 27. 2 times 27 is 54. So this equation will work for both sets of x, y. So that's great. The real world does not always give us such beautiful problems. So let's look at a real world problem. Real world data isn't as beautiful as that. Can be a little bit sketchy, so let's look at this data and make some decisions here. All right, so I have this table, and the table shows the numbers y and thousands of people who visit Machu Picchu X years after 1990, write a function that models the data. Okay, so let me show you something interesting about real world data, and you will probably want a calculator for this problem. So I first obviously want to look for that pattern in the addition in the input, right? So from 0 to 4, I'm adding 4, 4 to 8, I'm adding 4, 8 to 12, I'm adding 4. So I do have that addition, and you'll see that all the way across in the input. So there might possibly be a pattern in that output. So I'm going to check for multiplication first. So I need to know what multiplies by 150 to give me 210. To find that out, I would divide them. So 210 divided by 150 is 1.4. 360 divided by 210 is 1.7. 470 divided by 360 is 1.3. 700 divided by 470 is 1.4. So I'm multiplying by each of these to get to the next one. So 150 times 1.4 should give me 210. 210 times 1.7 should give me 360. 360 times 1.3. Now you'll notice a lot of people will tell me this isn't common. Now you have to consider the fact that this is real world numbers. So it's not going to be the best common ratio ever. It should be just close. And notice we do have some repeats. So this is very close. 1.4, 1.7, 1.3. These are all very close numbers. Another thing you can do is graph it, and you can see in this graph the way it's curving up like an exponential growth function. So the likelihood that exponential growth will work here is very, very high. So I'm going to go ahead and write an exponential growth equation that should best match this data or best model this data. It'll be close, not spot on. Now I want this to be exponential, so I'm going to go with y equals ab to the power of x. Again, I'm going to use 2 points, so let me just pick a point. I'm going to use this first point because I like a good 0. Zeros always fill me with love. So if I use the point 0, 150, I'm going to have an x here and a y here. So that means 150 is equal to a times b to the power of 0. B to the power of 0 is 1. So that means 150 is equal to the power, 150 is equal to a. That's fantastic. Let's choose a second point. So for my second point, I'm just going to use 4 and 210. You can use any points. If you use different points than me, your b value might be slightly different, and that's completely fine. But for ease, I usually just use the first 2 if I can. So y equals a times b to the x. That means 210 equals a, which is 150, times b, to the power of x, which is 4. Cool. Well, I'm going to divide both sides by 150. So I already know 210 divided by 150 is 1.4. So 1.4 is equal to b to the power of 4. I need to know what b is, so I'm going to have to take the 4th root of both sides. You will need a calculator to do that. And it's going to be approximately 1.09. So I'm going to go with that. It's actually approximate. Let's change that. It's approximately that. So that's what I'm going to go with. So I think my best guess equation for this is going to be y equals 150 times 1.09 to the power of x. And there's a few extra practice problems down here. If you want to press pause, go ahead and work those practice problems, then press play and you can check your answers. So go ahead and press pause, do these 2 extra practice problems. Then when you're ready, press play and you can see the solutions. Okay, so number 1 is going to be an exponential function, and it looks like the common ratio is going to be 3. So we did multiply by 3. The common ratio on that would be 3. The equation for this one that I got, and yours might be a tad bit off depending on what points you used, but I got y equals 25 times 1.6 to the power of x. You might have a 1.7 or a 1.8 or 1.5, depending on which points you used. All right, thank you so much.